Hello. The purpose of this week's lab was to analyze the motion of a spring mass system oscillating from left to right, and then compare that motion in the video to a computer model created with VPython using the energy principle and Newton's second law. The fundamental principles associated with this lab were the Newton's second law and energy principle I stated earlier, and these are the equations for Newton's second law, where V final equals V initial plus F net over m times delta T. I have the equations for the energy principle, with delta E equals the change in kinetic energy plus the change in the potential energy of the spring plus the change in the potential energy plus the change in the gravitational potential energy. To obtain the positions of the spring mass system's motion, we use Tracker to analyze the video. In Tracker, to analyze the video, I set up my coordinate system whereby my positive y direction is pointing upwards and my positive x direction is to the right. I started analyzing the video at the moment of its initial release, and here you'll see Tracker run. And I obtained x and y coordinates, which I copied and pasted into Excel to create a CSV file that I'll be using the Python code later. Before we can begin creating a computer model, I had to calculate the spring constant. The equation for the period is given as 2 times pi times the square root of m over k. And using this equation, we can calculate the spring constant for the spring mass for the spring in this experiment. To find the period of oscillation, we used the graph in Tracker and found the period for 3 oscillations and divided that by 3 to find the period for 1 oscillation. The value of K was found to be 6.83 Newton meters. I then had to calculate the initial length of the spring. To do this, I use the concept of static equilibrium, whereby the force of gravity equals the force of the spring. This gives us the equation mg equals k into L minus L naught, and to find L naught was simply a matter of rearranging that equation to solve L naught, and the value of L naught was obtained to be 0.12 meters. Once I had done this, I could then create a computer model for the motion of the spring mass system. I start with my initial conditions, entering the ball's mass, this position, and the velocity, and also entering this code block to read the CSV file I have created from using Tracker. I enter the gravitational G equals 9.8, the spring constant, and the initial length, as well as setting up L, which is basically ball dot pause minus spring dot pause. I put in the value for the kinetic energy of the ball's motion, which is half mv squared, and the potential energy, which is the mass times the gravity times this height, as well as the spring potential energy, which is half ks squared. I define my initial energies, as well as another formula for force of gravity and the force of spring. Using Newton's second law, I could then update the velocity and its position, as well as also updating the length of the spring and its compression. After doing that, I calculated the value of the kinetic energy of the ball, as well as the change in kinetic energy, the potential energy, the change in potential energy as well of gravity, and the potential energy of the spring. I also calculated the change in potential energy of the spring. Using the energy principle equation shown earlier, where delta E equals the change in kinetic energy plus the change in the potential energy of gravity and the change in potential energy of the spring, I found E and then graphed all these values to come up with the equation as shown when I run the code. CSV file I created from Tracker. I was then able to create 2 graphs to compare with the object's motion as shown in Tracker and the computer model's motion. The The object's motion is shown in red. The object's motion tracker is shown in red, and the computer model is in blue. As you can see, these two graphs don't really match up as well. However, they should in theory. The reason they don't match is probably due to an error in tracker when trying to find the plant mass while analyzing the video. Now onto the what-if questions. Is the energy principle satisfied? Yes. The energy principle states that the change in energy equals the change in kinetic energy plus the change in potential energy of the spring plus the change in gravitational potential energy. And since for this experiment we picked our system as the mass, the spring, and the Earth, we can assume, ignoring any effects of air friction, that no energy transfer occurs to or from the surroundings. This is confirmed in the Python model, as you'll see. Here we have the spring potential energy in red, and the gravitational potential energy in green, and the kinetic energy in blue, as well as the changing energy in yellow. Notice that the spring potential energy and the gravitational potential energy are out of phase. So when you have maximum spring potential energy, you have minimum gravitational potential energy, and the change in energy is 0, as you can see from the graph. Next, I had to do my period calculation for the x and y coordinate data in Tracker. Using the method I described earlier for finding the period using the graph in Tracker as reference, I obtained values of the period for both the x and y coordinates. In the x direction, I had my period as 1.61 seconds, and in the y direction, I had my period as 1.27 seconds. The period in the x direction is significantly larger than the period in the y direction because there is more movement or more oscillation going on in the x direction than there is in the y direction.